Let's look at another example and then recap all the main points. Here h of z equals z squared plus 1. And we know it has two zeros, one at I, another at minus I. We take a circle of radius 2 in order to contain the two zeros, and z goes around this circle just once. For every one of the zeros on the image side, first of all, let's split this apart. Z squared and then plus 1. The z squared would be 4 e to the 2I theta, because z is 2 e to the I theta. And z squared would be on the circle of radius 4 centered at the origin. Now if we add 1 to z squared, that will shift the circle of radius 4 where z squared is to another circle of radius 4 to the right, and that would change the center. The center would move to the right by 1 unit. Okay, so here's z squared plus 1. Now, when the argument of z starts at minus pi, the argument of z squared starts at minus 2 pi, and it moves counterclockwise. Okay, and after you add 1, it would move on this shifted circle. For the first 0, it moves around once, and then for the second one, another time. So it winds around the origin twice. Now, there are 3 main points I want to emphasize. First of all, this is for all examples and for all degrees and everything. When we know for sure there are so many roots in some big circle that contains all of them, going around that circle once, the image will go around the origin that many times, as many as there are roots. On the other hand, if it happens that the image winds around the origin so many times, there are the same number of zeros within that big circle. Now, the third and very important point here, and I said in the last clip that the power function is very important, z squared. Now, the highest power in this expression, in all of the polynomials, that's the one that dominates the rest of the polynomial, especially if you choose the circle large enough. When this circle is large enough, that highest power of the polynomial plays a dominant role. You can see over here, look at the z squared, and that adding 1 to it, because it's so small compared to the radius of the circle, that shifting z squared by a little bit is not going to change the fact that z squared plus 1, which is the whole polynomials, moves around the origin together with the dominant power, z to the highest power. And that's because we have chosen this circle large enough to make z squared big enough so plus 1 is not going to affect it. So for example, if that was plus 10, it will shift this circle way to the right. So then the winding would happen here on the side, and it will escape the origin, which is very important. This origin here in the W plane is the image of all the zeros. So it's important for the winding to happen around the origin here, the image of all the zeros. So these three main points combined will ensure that every time you have a polynomial of any degree, because the highest power has that winding property, the rest of the polynomial can be negligible and is just as good as just the highest power. It behaves exactly the same way. So because the highest power we know for sure has this many zeros, therefore the whole polynomial must have that many zeros. And therefore we can factor any polynomial. This concludes the polynomial factorization.